Hi, Tobias.
Hello, Arno.
It's a pleasure to have you here today.
Thank you. Thank you. It's a pleasure.
So today my guest is Tobias Achterberg. He's the Vice President of Research and Development at Gurobi. Tobias is the author of SCIP, currently the best academic MIP solver. In addition to numerous publications in scientific journals, he has also received several awards for his dissertation and for SCIP, such as the Beale-Orchard-Hays Prize. From 2006, Tobias worked for ILOG and later for IBM as developer of Simplex in versions 11 to 12.6. Since 2014, he participates in the development of the Gurobi Optimizer, and in his spare time, Tobias continues to work on the Gurobi MIP solver because he's addicted to mixed integer programming. According to him, he does not have any interest in other things. His spouse, his 3 children, his 2 drum kits, and his attendances in the moshpits of punk rock concerts are just mock-ups to pretend having a normal life. Tobias, thank you very much for being here. Such an honor. How are you today?
Very good. Thank you.
So Tobias, I hope I did not kill the pronunciation of your surname.
That's fine. That's fine.
Okay.
So Tobias Achterberg. That's how you pronounce it.
Yeah. So you were born in 1975 in Germany, but where exactly?
In Berlin, in the district of Tempelhof, Mariendorf. So this is where I grew up. So this is in the southwestern part of Berlin.
So it was like, yeah, West Berlin. Okay. So tell me a bit about your family background, starting with your parents.
Yeah. So my mother was born on August 6, 1945. So the exact day of the Hiroshima bomb, which was always a big thing for her, and she always wanted to go to Hiroshima at some point, but unfortunately she never made it in the end, because then when she got older, like after 67 or 68, she got a Parkinson, and it was pretty heavy, and relatively soon after, a few years, then she died. My father was born 1 year earlier, 1944. He is still alive, luckily, so that's good. And he is also a mathematician, but working on a completely different side of mathematics, namely on the very much fundamental basic theory, like set theory and categorical theory. He was also then working as a professor at the Technical University Berlin, where I was studying, so that was kind of an advantage for me to have him being there. But I never took any classes with him. So.
Okay. What did your mom do for a living?
So my mother was also a mathematical and computer science background. So she was a mathematical assistant. That was the name of the position, where she was implementing and coding stuff first for a company called KWU, so Kraftwerksunion, and they were then at some point bought by Siemens. So she was then a long time Siemens employee, and then also helped to introduce the SAP at Siemens and all that. So she was in the business area where they were dealing with energy production, gas turbines and stuff like that.
So she was a software developer, and
yes,
your dad was a mathematician.
Right.
Yes. So you're probably
she started coding with punch cards and all that, and then also later in COBOL. I don't know if you know that language.
Mm-hmm.
And then later she went more into this SAP stuff.
Yeah, I think you were definitely a convex combination of their background.
Essentially, yes.
Yeah, very nice. Did you have brothers or sisters?
Yes, I have 2 older brothers. So my oldest brother, Andreas, he's a teacher, math and physics. Mm-hmm. And the middle brother, Florian, he is actually a math professor now currently in Denver. And he is working on graph theory, so with, in particular, infinite graphs.
Wow.
So related to what I'm doing, he's actually sometimes using Gurobi for his work.
How cool is that? Fantastic. Yeah. So a family of mathematicians, and yeah, that's fantastic. So you were born during the Cold War. What are your memories from that period?
Yeah, so of course, the memories include like having this wall around your city, but in the daily life it doesn't affect you that much. It's just sometimes you go to the wall, step on these outpost looking things, and look how it is looking behind the wall. Where it matters the most is when you, with the family, when you have vacations, and then of course you go into that traffic jam in front of that of the border, where you have to wait an hour and a half, 1.5 hours, 2 hours, or something like that. And then you from the West Berlin, there were, I think, 3 different highways that go straight to the western part of Germany, and you have to stay on those highways. You are not allowed to go somewhere else. So you go straight, and there's this 100 kilometers an hour speed limit, so which is rather slow, but this is the things that you remember. And
Yeah, you had relatives in the east side?
yes, I do. I do have relatives on the eastern side. So the sister of my grandmother, she was living in Dresden, so we visited her pretty often. So that was nice. And we also, from my father, we have relatives in a small town close to Berlin.
Mm-hmm.
So, and of course, we sometimes also went to East Berlin and looked at that. And when you go to the eastern part of Germany, you were forced to do this money exchange. So convert 100 West German marks to 100 East German marks, which were of course much less valuable. And then you have to spend the money there because you basically cannot bring it back.
Yes, yes.
So those are the things that I remember. And then of course, 1989, when the wall came down on November 9, I do remember still that when we heard that in the news, my mother was completely excited and said immediately, "Yeah, now we need to go to Checkpoint Charlie and look what's happening." And I remember that the middle brother, so Florian, and me were still at home, and we were like, "Oh no, come on, we can see that much better in the TV. Let's stay here. We are too lazy to go there." And so right, so now looking back, I was really disappointed that I did that, because now of course I'm missing that memory. But back then I was 14, right? So I was like, "Oh no, come on."
Yeah, I can understand. Yeah. So, how was your history classes regarding the First and Second World Wars? How did they portray Germany?
Yeah, so First World War in history classes, of course, you cover that, but that was mostly maybe once or twice in the whole school system. Relatively boring, I would say. But of course, Second World War, that appears multiple times. I think we had it like 4 different times throughout the whole school system, with all the different aspects, like how Hitler came to power, what happened to the Jews and other people, and then also the war itself, the different the other countries, so France and the USSR and England and Great Britain and US and so forth, and how this happened. But of course, the largest aspect was the Holocaust. And then, of course, you also visit these memorial sites with the concentration camps and so forth, which is pretty impressive. So there's one close to Berlin which you can look at, which is really impressive. And still, so today, still the pupils are still doing that. So I know that from my kids, of course, the topic also comes up. But this is super important, and I'm glad that we cover it so well in the school system that you really know what was going on.
Yeah. I visited the memorial in Berlin. They have, right?
Yeah, the one in the center of Berlin.
Yeah.
That is just an artwork.
Yes, I know.
Right?
Yeah, sure. Not the actual one, of course.
Yeah. Not the concentration camp. So if you go to that concentration camp and look how this looks like, you really kind of feel, wow, that was really evil.
Yeah. So you had to do a brain surgery when you were 17.
Yes, indeed. So when I was 17, which was kind of in the final stages of my high school years, I before that, so I had this kind of strange issues with my vision, so some double pictures and so forth, and then I went through various doctors and all that, and weeks I spent in hospitals, so 1 week here, 1 week there, just to try to find out what's going on. So and when I was, I was 17, and hospitals in Germany, back then they were already overcrowded often. So one situation I remember was that they didn't have enough beds anymore. So I was put into some kind of cleaning cabin or so with with a bed for the night, stuff like that. And then eventually they found the issue. I had a tumor in my vision nerve, right? So not cancer, so the good or more good tumors. Which was pressing on the nerve, and that was hampering with my vision on the left eye. And then they tried to remove that. So they did a surgery, cut off my head up here, pulled up my brain, put it on top of it, and then go from the top to my left eye and try to cut away this tumor. But unfortunately, it was already too late. So the nerve was too much damaged. So that means I'm now blind on my left eye, which is also the reason why it also looks like a little bit strange here. Yeah, but other than that, so of course my mother was terrified, right? So strange thing. So when you are young, you feel you are kind of immortal. So I didn't have any panic for the surgery. So my mother had much more like that, and it all went well. But yeah, they didn't succeed to save the.
Can you
vision.
drive?
I would be allowed to drive, but I never made a driver's license, right? So when that happened, it was close before I was 18. So all my friends made their driver's licenses. So and then I could always go with them, and there was never a need. And I'm also like, I have fear of speed. So driving a car is not really driving myself a car. So going with somebody else is fine, but being responsible for that's not something I would like to be. Yeah, and then in a city like Berlin, you actually don't need a driver's license. So the only thing that is kind of bad is sometimes when we go on vacation with my spouse, then it's always her who has to do the driving. I cannot help her, so that's bad. But other than that, it doesn't impact. So really the other thing about blindness is just on one eye. Of course, 3D movies I can't watch, right? And then the other thing is in social interaction, sometimes it's strange, right? When I talk to someone, then people always say, huh, me? Because they don't understand that I'm looking at them because they think this eye is looking at someone else. So there's always that regularly leads to some awkward situations. Yeah. But other than that, I don't have any.
Yeah, you got used over the years, and you just learn how to cope with that. I understand. I'm aware you were a drummer. When did you learn how to play?
Well, so an amateur drummer, so I'm not really a professional. But so I got kind of addicted to drumming when I was, I don't know, 10, 11, 12 years. So my mother took me to a Christmas rock concert at some school where a friend of us were singing in the choir. And I was then immediately going to the front row and sit in front of the drummer, and was so amazed by that from that point on I always liked to drum. So always like also in the kitchen with cooking equipment and so on. I was drumming and so forth. But I never took lessons. So and I never started to actively drumming with a drum kit. It only started when I think when I was 35 or so. Then my wife was giving me an electrical drum kit as a present, and then I started to play, and then from that point on, I did that very often. So play along with some music that I was listening on from the computer or from CD or something like that.
Yeah, I know you like punk rock bands. So
yes,
which are your favorite punk rock bands?
Yeah, so the two most favorite ones for me are two German punk rock bands, which are Die Ärzte and Wieso. So these are the ones I really like to go to concerts and so forth. And I also like Die Toten Hosen, which is another German punk rock band, which might be more well known also in other parts of the world because they play quite often also in Argentina, where they, for whatever reason, have a large fan base. In any case, but I also like US punk rock bands like Bad Religion or Green Day, if you call that punk. So one thing about Green Day is I was listening to them when they played, I think it was in 1993, as a support band of Die Toten Hosen. This was the first time so they were not yet famous, right? I think they just had released their Dookie album, and they were playing that, and I was like, oh, that's a nice band. So nice support band. And then later they became famous. So that was nice.
That's very interesting. So is it true that you started coding in BASIC at the age of 10?
Yeah, I don't know anymore whether it was really 10 or 11 or something. But so when I was 10, my mother gave us a Commodore 64 as a gift. So actually, I think my brother Florian got the Commodore 64 and I got the floppy disk drive. So both of which were, as far as I remember, a 500 Deutsche Mark value. So the floppy drive was as expensive as the computer. And then from that point on, I got addicted to it. And I was, of course, playing games and so forth. And then at some point, my mother was like, yeah, so he's always spending so much time on that with playing games. So let's teach him to do something more useful. And then she started to teach me coding in BASIC. And the first thing that she taught me that she implemented together with me was a pen and paper game that we always played back then, where you have a grid. And one player would place certain things in that grid, and the other player would try to find out which of the cells are marked. Because the other player can shoot rays into, and then with certain rules, the ray comes out, and then the player who has placed it tells where the ray comes out, and then you have to do logical induction basically to find out where the things are. And this is what we then had implemented on the Commodore 64 in BASIC. Of course, the computer was placing these marks, and the player had to shoot rays.
That is incredible. I mean, at the age of 11, 10, coding all this stuff, I cannot just picture that.
And then the next one, I've coded alone, was actually the Rubik's Cube. So I did, and then I not in 3D. I did what I later learned was a 2D projection. You know, this thing which looks like a T-shape thing, and then the player could say which direction at which point they want to rotate, and then the rotation would be applied.
Wow! So you were really addicted to computers.
Yes, very much.
You have a master's degree in mathematics and in computer science, correct?
Indeed.
Yeah. So I mean, it was not hard to choose. Maybe it was actually hard because you did both in the end.
Yes. So I did both. So because I could decide, and it was clear I need to do something with math. So it was always clear. And then there was this computer thing that I enjoyed so much. So I tried to combine it, and then I came to the conclusion, I should just study both. And in the end, it's not twice as much work, because you can always take the classes of one as the also as partial classes for the other. So like, computer scientists need to do math for computer scientists. Of course, I could just take my math studies instead as a replacement and so forth. So I would say it is like 50% more work plus the additional master's thesis that you have to write.
Okay. When did you first learn about optimization?
Yeah, that was of course in the university. When I was finished with my what is called Vordiplom, so nowadays you would call it bachelor, I guess. Then I was looking at what kind of specialization should I do, and then my father, who was working at the technical university, told me, here there's Martin Grötschel. This is the superstar. You should look at his classes. And then and luckily, so Martin Grötschel's cycle just started, so with linear programming, and then I went into that, and that got me into it, and then since then I'm addicted to that as well. So and we had, yeah, this was a 3-semester thing, so linear programming and then combinatorial optimization and then something else.
Yeah.
And actually, it was also in my math classes with Martin Grötschel where I learned how to code in C. So it was not in the computer science classes. There we had other programming languages, but the math stuff that was done in C. And then one of the things that I remember is that we had that task to code a Simplex algorithm. I think the linear algebra was given to us, so I don't remember implementing an LU factorization, but of course all the pricing and ratio tests and pivoting and stuff like that. And actually the most difficult part of the whole exercise was the parser for the LP file format. And the nice thing, I was doing that together with Utz Uwe, and he knew Bison and Yak and Flex, all those parsing things. And so we wrote a formal language in that thing for the LP file format, and then he had the parser, and I did the pricing and algorithmic stuff. So, and then we had it. So that was a nice exercise. But then, of course, afterwards, then we compared our results to what to CPLEX. I think it was back then. It was probably version 6.0 or 5 point something. And then you see, oh, hey, maybe our Simplex algorithm is not that good. You can do it better.
Yeah. Yeah, I also make my master's students code a Simplex algorithm. I usually I let them choose. They can use the revised Simplex or the one they feel more comfortable in. And parsing is a recurrent issue. So I understand your point perfectly. So what was your first master's dissertation about?
So my first master dissertation is in math. So I did that in 2000. And this was about the so-called arborescence flow problem. So this is a problem that appears somehow in telecommunications, because in a TCP/IP network, the routing rules are such that all the routes that go to some, so from one point to another, need to follow a shortest path according to some distance measures that you have installed on each of the network nodes. And that leads to the concept that all the paths need to form an arborescence. Mm-hmm. So you cannot join flows again. And that is, I did theoretical work on that, so finding facet-defining inequalities and proving that there are facets and stuff like that. And I also constructed some problem instances and tried to solve them. And this is why the two instances aflow30A and aflow40B in the MIP exist. So they came from that, from that thesis.
Very interesting. What about your second master's dissertation?
So in computer science, I did 1 year later. And there, so my topic in computer science was artificial intelligence, which is really interesting. So even back then, it was interesting. And I wanted, but I was already working at the Zuse Institute already due to my master's thesis. And I was so addicted to optimization, I wanted to kind of continue optimization. And I tried to find a topic that would fit. And then I decided it is a good and interesting topic to try to learn with machine learning techniques, a branching rule for mixed integer programming. So, and I had the luck that Alexander Martin, who had been at the Zuse Institute before, but he already left when I joined there, he had implemented a mixed integer programming code called Solving Integer Programs, so SIP. And he allowed me to use that code to do my studies. And together with Thorsten Koch, I then started to do that and hacked away. And I basically did back then what nowadays became also pretty popular, like which is extracting some features from each node and then try to learn what happens to the objective when you branch on a certain variable given on that feature. And then I use different techniques to try to learn this this mapping, so it's like support vector machines, mixture of experts, neural networks, radial basis functions, and a few others. And the hope was that this magically finds us a good combination of features that allows us to select the branching variable. And actually it did, but it was still kind of disappointing, because what most of the machine learning techniques then told me was, yeah, you just need to look at that one particular feature. All the others do not matter. And this one particular feature was one that I invented, which is kind of pseudo costs plus a bit more, which I back then called the history value. And that gave then was then the origin for this paper with Alex Martin and Thorsten Koch, Branching Rules Revisited, which is this what is now called reliability branching.
Yeah, that's a very
So
famous
this was
paper.
basically the outcome of my whole thesis. So kind of ignore all the machine learning stuff. Here's the good feature.
Yeah. So that paper appeared in oral letters, right?
Yes, indeed.
Yes. It's well cited. I'm familiar with that work. And you mentioned the SCIP solver. I mean, you're in good company, by the way, with Professors Martin Grötschel and Alexander Martin. You already had the influence of your parents, so well,
Yes.
that was very good. But your PhD work was about the SCIP framework. So tell me the story behind it.
Yeah. So this was when I was then working with ZIP, and at some point, after my computer science thesis, I then thought, what should I do for my PhD? And then the idea was, so I was already in touch with constraint programming from my computer science studies and stuff like that, and I was thinking, this is basically the same as mixed integer programming, just looking at the same thing from a different viewpoint. So why can't we just combine that? Which is actually the same idea that John Hooker had back then, but I didn't know about his work. So I started to think about how to combine it, and then I wanted to implement the framework to do so. And then I realized that with ZIP, the data structures are so much specialized to mixed integer programming, where the LP relaxation is so much the central core of the data structures, that I couldn't integrate all the constraint programming stuff and the more general constraint types into that code. And that is why I then started over from scratch. And because of the heritage of ZIP, I decided to call that SCIP, so solving constraint integer programs. That's how it started. This was in 2001, where I had, I think, my first commit to back then it was still a CVS repository. And it quickly evolved. So, and the great thing about working at the Zuse Institute back then was that Martin Grötschel gave me the complete freedom to do that. So there was no other task that I had. So maybe there was once in a while some projects that I had to then kind of deal with, but not really. So I could almost exclusively focus on that coding. And for several years, I could code without any main interruptions. And that is how all these 100,000 of lines of SCIP source code came about that I ended up with. And then the next very nice and lucky thing that happened was that exactly at the right time, Martin Grötschel was connecting me to an application where constraint integer programming was a very good fit, which came from an industry partner where Grötschel had worked with before, namely Infineon, right? So in the past, Grötschel did this TSP stuff for chip layouts, so for the drilling of these boards, so finding the shortest tour so that the drilling can be fast. And so he had contacts with Infineon, and now they had a different problem, which is chip design verification, which means you need to prove that your chip design has certain properties. And in order to be able to prove it, you have to show that there is no counterexample, and that leads to a constraint program where you need to prove that this is infeasible. And they had very good software based on SAT solvers to deal with all the logic in these chips, but they were struggling with arithmetics. So with arithmetical logical units, when they have addition, multiplication, division, and so forth, then the SAT solver would no longer be able to solve that. And this was really where the combination of constraint programming and mixture programming could get in. And so I tackled that problem with them, and that was very successful and led to, I think, another 150 pages in my PhD thesis to just describe that one. And that was nice, yeah. And because of that, I also learned a lot about satisfiability solving. Mm-hmm. And one nice thing was, another nice coincidence was that at that point, a researcher from Minsk in Belarus, so Yakov Novikov, wanted to go to Infineon to work with them, who are in Munich. And for whatever reason, it was easier for him to go through Berlin and then from Berlin to Munich. And so he stayed 1 or 2 days in Berlin, and then and Grötschel asked me to pick him up at the train station and get him to the Zuse Institute. And so I did, of course. And it was funny. So when we were meeting there at the train station, then he told me, yeah, directly after I left the train, I got marked by some people, right? Because of course, when people come from Eastern Europe to Berlin, in particular like Belarus or Ukraine or Russia, and look like that, those are the business people who have like millions of dollars in their suitcase and to buy something here or whatever. So he got marked, and they wanted to get his money, but then he could prove by showing his research papers that he is just a poor scientist. So they left him alone. And then we took the subway to the Zuse Institute, which is roughly a 30-minute drive. And in the subway, he explained to me how conflict analysis works in SAT solvers. So how you would, when you hit an infeasible subproblem in the search tree, how you would analyze this infeasibility to derive additional constraints that you can then later use in the search to do more propagation. And I was really interested in that, and then I generalized that to mixed integer programming. And that was why I now have this paper about conflict analysis and mixed integer programming. And this, I implemented that in SCIP, of course, and nowadays all the solvers, so Express, Gurobi, CPLEX, all have conflict analysis as a tool in their arsenal to get faster performance.
Yeah, you did an amazing work in your PhD, very influential. Of course, as I said already, you had good company and some events like this that triggered new ideas, and it's just fantastic. SCIP is now fully open source, right?
Yes, nowadays it is actually, but it for a very long time it was not. So this is really recent that they went to a fully open source license, so which means you can also use it for free, also for commercial purposes. For the most of the time, SCIP was only under the so-called SCIP academic license, which means that academics can always use it for free and can also download the source code and everything. But commercial users were not allowed without paying money. So, and I think back then it was kind of good and fair, because the rationale behind it was that SCIP was developed with the help of state money, right, research funding. And so it shouldn't make competition to commercial solvers. So commercial solvers should also get their money and not just dumping something out for free, which was funded by state money.
Yeah, you did not have to code the linear programming solver from scratch, right?
No, I never, except for that exercise in my classes, I never wrote a linear programming solver myself. I could, so SCIP was implemented to link either to Simplex, which was written a few years before by Roland Wunderling, also at Zuse Institute Berlin, or Simplex. And there was an interface that you could just swap out the LP solver.
I interrupted you, Tobias. You wanted to complement what you're saying, or it's fine?
No. I just wanted to continue with the licensing. And then people were always there was a confusion. So people were saying, yeah, that's an open source solver, but it was not open source in the sense of the Free Open Source Foundation, because it was not allowed to be used for commercial purposes. So that was always a little bit of a hassle. But now the new maintainers of SCIP decided that now it's time to make it completely open source, and now everybody can use it. So
Okay.
that's very nice.
Very nice, absolutely, yeah. How did you end up working for ILOG in 2006?
Yeah, so when I was done with my work on conflict analysis, I went to the MIP workshop. So I guess you know that. This is a really nice workshop for people working on mixed integer programming. And this was in 2005. And this workshop was in Minneapolis, which was back then called the IMA Hot Topics Workshop on Mixed Integer Programming. And I went there and I had this presentation on my laptop about conflict analysis, but I didn't have a slot in the program. And so I don't know for sure, but I think that Martin Grötschel kind of used his power to convince the organizers that they have to squeeze me into the program. And so at some point, suddenly my talk appeared in the Thursday evening slot. And then I could give this presentation. And part of the presentation was also the performance, just the regular performance comparison to CPLEX. And it was back then when the SCIP linked to CPLEX as an LP solver was pretty much of similar performance as CPLEX 9.0. And back then, CPLEX 10.0 was very new. So 9.0 was almost the most recent one. And Gu, so Songhao Gu and Ed Rothberg were sitting in the audience back then. And after my talk, they approached me and asked me, yeah, do you have already any plans for what you do after your PhD? And then I said, no. And then they were saying, oh, well, why don't you come to ILOG? And then I said, yeah, why not? So, and then I guess 1 year later, so I was then traveling to the ILOG offsite meeting, all company offsite meeting, which was back then in where was it? So close to Nice, and that what's the name? In that small town which is famous for the cinema festival.
Cannes?
Cannes, yeah, in Cannes. That was in Cannes in a nice 5-star hotel. And at some point, I went in there and looked at. There was the big table where everybody was sitting around and was then talking to those folks. And then a little later, they gave me an offer. Express, so back then it was still Dash optimization. They also wanted to hire me and gave me a counter offer, and then it went back and forth and back and forth. And at some point I was like, oh no, come on, I don't need any more money, so that's enough. I have to base my decision on other things. And then at some point, yeah, I was just from my studies, I was used to CPLEX, so I liked it a lot. So that was kind of my thing. So I decided to go with ILOG. And then in November 2000, or no, September, October 2006, I joined ILOG, but I still was not done with my PhD thesis. And then the thing is, I already had one son who was born 2004. And in November 2006, my daughter was born. And that was exactly the time where I had a full-time job at ILOG, plus I had to write my PhD thesis, so which means I had like 18-hour days, including the weekends. So luckily, then my wife was taking care of the kids and did everything, and I could focus on my studies. So I'm very thankful still to her to do that. But the unfortunate part is I basically missed the first month of my daughter, so, which is unfortunate. But that's how it is, right? So
Yeah.
with kind of writing your thesis while you're already working, it's not something that I would propose everybody should do. So that's tough.
Yes. I was when I was finishing my PhD, I started teaching too. So I didn't have kids, but it was already very busy. I can imagine your case. It was very, very demanding for sure. What were your main contributions to the Simplex solver?
So of course, when I started working for CPLEX, the first thing I did was working on the branching rule to include this reliability branching. Actually, Ed so Ed was actually not working on CPLEX back then. He was working on a different project with some chip manufacturing process. So it was only Gu who was then at CPLEX, and of course many other folks. And Gu wanted thought about implementing that himself, but he then thought, well, Tobias is joining, so let's keep it for him. And so I did that as my very first project. And then the next thing I think was conflict analysis, of course. So I just implemented everything in CPLEX that I knew from my SCIP worked. So I had a large set of things, and I just had one success after the other. So that is always nice. When you hire someone who has implemented their own solver, then they have a large arsenal of things that they know just work, and they can just implement them, and it will usually be a success. So that's nice, and this happened to me as well. And then at some point, things get a little bit tougher, right, to get performance improvements. So I was then working on cutting planes, MIR cuts, and so forth. So I did basically, and pre-solve. Pre-solve is always a large thing, and it's also pre-solve is the most fun part of the solver to work with, because there, when you have an idea that is reducing the problem size or finding something, then typically you get a performance improvement out of it, which is for branching rules and cutting planes by far not the case. So even everything looks great with your new cut. It cuts off the LP solution, tightens the bound a lot, and still performance sucks. So this can happen with cuts. With pre-solve, that's usually not the case. So this is nice. Yeah, and over the time, I basically worked on all aspects of the mixed integer programming part of the solver, except for the LP relaxation. So I never worked on the Simplex or barrier algorithm.
Mm-hmm. Yeah, I have used Simplex extensively, still to this day use. So probably we have somehow, a lot of people have been influenced by your innovations and your code. So that's very cool, I think, right? To imagine that. So IBM acquired the ILOG at some point, but then you left IBM in 2014 and joined Gurobi. Why?
Yeah, so it was actually triggered by the divorce that I had. So by splitting up with my wife in 2013, and then at the end of 2013, I was kind of so depressed, and I needed just a change in my life. And a big part of my life was, of course, the work, and so it kind of felt natural to change that. And Bob Bixby already approached me a few years earlier and asked me whether I want to join Gurobi. And back then I was, no, so CPLEX is my baby, so thanks for the offer, but I stay where I am. And the CPLEX team was so great, and I didn't want to leave them. But that now was the time, and I called Bob and said, yeah, is your offer still there to join Gurobi? And he said, yes, of course. And then I did that. And also with IBM, you know, the CPLEX team was super cool. So a lot of nice people, very good friends, and so I really liked it there. But without the personal struggles, I would have stayed there just because the team was so great. And I'm now lucky that some of them now also joined Gurobi, so I can continue working with those people. Unfortunately, not all of them. Some of them also went somewhere else. So some of them went to FICO, some of them did something else. But a few friends from back then I'm now again colleagues with, so that's great.
Yeah, so you got to work with them again, and it should be, of course, a pleasure for you. How's the experience of working with the co-founders of Gurobi, like Zonghao Gu, Ed Rothberg, and Bob Bixby, and also with other names like Ed Klotz?
Yes. So Ed Klotz came. He's one of the people who then later after me went from CPLEX to Gurobi. So he is great. But actually, one of the other main reasons for me to join Gurobi was the possibility to work again with Gu and to also work for the first time in my life with Ed Rothberg. So Ed Rothberg was already, I had contacts with him back at CPLEX because he was present when we had the offsite meetings and discussed new ideas and stuff like that. And Ed was one of the main contributors for new ideas as well back then, but he never worked on CPLEX when I was there. So I never had kind of this daily interactions with him. And, you know, so Ed Rothberg really is a genius. So, and it's so exciting to work with him and collaborate with him. So that was also one of the reasons why I then joined Gurobi, just to be able to work with these guys. So Bob Bixby was not coding anymore at Gurobi. So he was then already the CEO of the company, and he did all the sales related things and organizational things. So I never had experience with working with Bob on the code, also not at CPLEX. So he was already done with coding when I joined CPLEX. So I don't know what how he is implementing stuff, but it must be good because he had such a big success.
Of course.
But anyway, so I was working with him in terms of also discussing ideas and stuff like that, because he was still very knowledgeable about all the interior of Simplex and stuff like that. So that's always valuable.
Yeah. What is your main role at Gurobi, and what are your main contributions for the solver?
So right now I am what is called the Vice President of R&D, which means I'm leading the development team. And my main contribution still is the performance improvements of the MIP solver. So I'm continue to work on all aspects of the MIP solver, may it be branching, cutting planes, pre-solve, the whole tree framework, and parallelization, and stuff like that to improve performance. I also was very much involved more recently when in version, I think 9 it was, when we introduced the non-convex MIQCP solver. So I did most of the work to manage these non-convex constraints in the tree search and with the LP relaxation and all that. Other people contributed as well. So for example, this nonlinear interior point solver that was implemented by Robert Lutze, my colleague. But it was really nice to work on this thing, because it was something new data structures. I really love data structures and clean design of data structures. So this was a nice thing to be able to design that and then plug it in, and then everything worked out beautifully. So that was a nice success and very rewarding.
Mm-hmm. Another important contribution of yours is that you convinced the people at Gurobi to use Git.
Yeah, that's actually true. So that was one of my main, I would say, and earliest contributions when I started with Gurobi. I think back then they were using SVN subversion, and I convinced them to switch to Git, which was easy because Ed and Gu are very reasonable persons, so they just saw what the advantages are, and then we just did it in a relatively short amount of time. And from that point on, we are using Git. And then later we added GitHub on top of it. So this, web-based system to create issues and comment and work on those things, which we are still using today.
Yeah. So Tobias, you had the experience of developing open source optimization software with your very successful SCIP framework, and then you worked for ILOG, IBM, and Gurobi. So one question that I ask some of the guests is their impression on those that develop open source optimization software, in the sense that do they receive enough credit for such contributions?
I don't know if I can answer that from my personal experience. So I certainly did get enough credit for my work on SCIP, but other people may not. So for example, there is currently Hays, a very good open source solver developed in England.
Yes.
So they also get a lot of attention, but I don't know if they get enough credit or whatever you would say. And then there was a CBC, right? So, and CLP that also is well known. I don't know if John Forrest cares much about getting credit for anything. I think it's also he just loves to implement stuff, and that's the thing. I don't think just like me, he doesn't need any credit. Yeah, so that's. But this is a tough thing. But maybe it's not so much about getting credit or.
I'm saying appreciation from the community, and at times in academia, they have to come up with fancy papers, and
that's the point. So when you are an academic, what you usually need is you need to write a paper at some point about your thing, and writing papers about practical computational work is really tough. And this is, I think, what where we have an issue as a community, that computational work is not appreciated as much as it should be, at least compared to the effort it makes to write a computational paper and to write the code to do that. You don't prove usually you don't prove theorems. You just take something and do it and then show that it works. And then this is a struggle, also partly due to the commercial solvers, that then often the reviewers would just say, yeah, why don't you run it with Gurobi? But that's not the point, right? You want to just show that your technique improves kind of what has been there before, for example, in SCIP. And but still people then would say, no, if you are not beating Gurobi or Express or whoever, then it is worthless. Yeah. And that is really painful.
Yeah, exactly. Very frustrating. Yeah.
Yeah. And the thing is, the advantage that we have on the commercial side for developing this is so huge that academics just cannot compete. So we have right now at Gurobi, we have 192 machines, a cluster of 192 machines where we can do our benchmarking, that those machines run 24/7 the whole day on full load. We always have something to test. And we have the luck that we do not need to do stuff that you can then later write a paper on. It could just be that we change the 10 to the minus 8 to the 10 to the minus 5 in the branching rule, and this gives 2% performance, and that's it. We are lucky, right? This is nothing that you can write a paper about. And this is the MIP solver development includes so much of software engineering tasks, and that this is stuff that you also cannot write a paper about. So you only can write a paper about the research, but kind of in comparison, I would say the time that we spend on research is maybe 10%, and 90% is then the software design, exactly, architecture, bug fixing, and then benchmarking and tweaking it until it eventually works. And that is tough for researchers to do.
Yes,
because they don't have that much time to do it, and they don't have a large team that can help them with doing it.
So Tobias, now I'm going to ask you some questions regarding MIP solvers. I mean, I already asked some, but now I'm going to bombard you with some more. Tell me everything you know about branching, including branching rules, strong branching, and so on.
Yeah, so branching is a really interesting topic, but in the end, at least this is my experience, what works best is just pseudo-cost branching with strong branching combination, so this reliability branching, and then you would have other criteria as a tiebreaker thing. So this is how it is done in SCIP, and this is also how it is done in Gurobi. And Gurobi, it's a little different. We have more hierarchy. In SCIP, there is a weighted combination, but with very tiny weights for the other things, and essentially still tie-breaking. But you need to do this tie-breaking for those problem instances where the objective function doesn't tell you much. It's just maybe a pure feasibility problem, or you just don't have objective increases and so forth. And then you have you're looking at other things like what we call pseudo shadow cost branching. That's another nice rule. And then you're looking at implications. So how many bound strengthenings you can do after branching on a variable. You're looking at what we are looking at also is what we call the active domain size of a variable. So we do statistics on each variable. What values did they actually take in all of the LP solutions, and then that is then the active domain, and the variable that has a larger active domain may be a good or a bad branching candidate. I don't remember anymore. And then more recently, there's actually an upcoming paper from a SCIP colleague, Mark Turner, who was investigating whether looking at the violation of a Gomery cut. So you look at your fractional variable, you produce a tableau row, and then kind of calculate the Gomery cut, and that is of course violated. And then how much it is violated, that could be used as a criterion for branching. That is, and I implemented that in Gurobi, and it worked a little bit, so it helped performance. So that is now also will be in the next Gurobi version. So that is another improvement there. And then I sent an email to Mark saying, yeah, your idea was working. So by the way, and he was saying, yeah, we also did that in SCIP, and it worked great. We're writing a paper together with, I think with Timo and Thorsten. So with Timo from FICO, I guess they are implementing that as well. So that's a nice new thing in branching rules. Other than that, the other thing what I would always like to stress about branching rules is that most fractional branching, so that means branching on a variable that is currently closest to 0.5 in its fractional part, that is the worst rule you can ever think of. And that is also one of the successes of this Gomery cut branching, because that you can use as another final selection rule when you run out of ideas to avoid that most fractional branching part.
Wow, that's I know that some people teach that, right? That's like common sense to go for the most fractional, but in the end, as you mentioned,
it's terrible.
It's terrible. Very interesting.
It's not better than random.
Wow, fascinating. Well, what about primal heuristics from MIP solvers? What do you think are promising avenues of research?
Yeah, so a big area of research which is right now really active again is large neighborhood search. So try to formulate a sub-MIP that you solve that covers some parts of the search space. And this is also the most important and successful type of heuristics in Gurobi. So the prime example is RINS, right? So this relaxation-induced neighborhood search, where actually this is a nice. In 2005, when I was at that MIP workshop, and Ed and Gu were there as well. So Ed had a talk exactly about RINS. So that is a nice coincidence here. Yeah, that is the most important ones. And then the problem is what to do with other things. So how to find a first feasible solution, because usually these large neighborhood search heuristics, they need some incumbent solution and then derive some neighborhood from there. And that is tough. So then there is, of course, diving, fix and dive with various selections of which variables to fix first and so forth, and to which value. Then for the non-convex MIQCP part, there's something interesting that I like that we also implemented in Gurobi is I think what Timo was working on was the so-called undercover heuristic. So you try to find fixings that for each product term you fix at least one of the two variables, and then the resulting problem will be a mixed integer linear program, and then solve that as a sub-MIP. So this is a nice one. And then more recently, we at Gurobi we hear from customers over and over again that this what we call the no-rel heuristic, that is a very useful tool. So because sometimes you have big problems where even solving the initial LP relaxation is too hard, so it already exceeds your time limit. And then what can you do? Then typical approaches to find solutions are just falling apart, and this is where this no-rel heuristic comes into play, because that kind of tries to find a rough approximate solution, and from there form small sub-MIPs, and then only iteratively solves smaller sub-problems, and then tries to combine them into a full solution. It is often very successful. So that was a very nice idea from Ed Rothberg, who implemented that initially, and then we extended it and it's parallelized and all that stuff. So that's also interesting.
What do you think of automatic decomposition?
Yeah, that's another interesting topic. Something that we recently kind of added a very specific type of automatic decomposition, not what you are thinking, not dancing wolf stuff, but what we did recently together with Pierre Bonamy was to detect neural network structure in a model. So when you have a neural network and model that as a MIP, then you will see that the layers of the neural network you can find as blocks in the coefficient structure of the matrix, and that means that you need to find those because you want to go with OBBT, so with optimization-based bound tightening. You want to go from left to right and from right to left through the network and get that order. And in order to do that, you need to identify the layers in the network, and that is a kind of decomposition algorithm, so a clustering algorithm that we implemented to find those, which was actually inspired by the one paper from Matteo Fischetti. They have this neural network which detects digits, handwritten digits, and you want to have an adversarial problem that says, yeah, here this picture is wrongly detected by that. And there, Matteo and co-author also did this OBBT through the layers. Of course, they knew the network structure, and then the idea was, yeah, what if we only have the MIP? We have to recognize the network structure. And so that was nice. But more, other than that, I, of course, know the work from Gerald Gamrat and other colleagues for this GCG project, which is part of the SCIP suite, which is also from Marco Lübecke. He is very much involved into that in Aachen with his students, which they have kind of mixed results. So for some problem classes, it works really great, and then they can do this Danzig-Wolf decomposition and solve things much faster than a MIP solver. For others, it produces garbage, so and that is tough. So I don't know yet how to get that kind of into the default settings of a solver to make it work. And on the other hand, in practice, maybe in most cases, the user already knows the partitioning and can just provide it to the users. This is currently our Gurobi approach, that we just provide an interface where the user can tell us what the components are. And then we would try to exploit that in a heuristic fashion.
Right. Do you think it's worth developing a commercial branch and price solver?
Yeah, so that is a tough question. So, the big commercial success of MIP solvers comes from the fact that this is a black box thing that people can use who have no clue about algorithms, who just know a bit about modeling. So who can model their business application, write them variables and constraints and then just plug it in and get a solution out. So this is why this works so well. For a branched cut and price solver, in my view, can only be a framework, because the pricing rule and then the cutting planes that would exploit the pricing rule, they need to be hand-tailored to that particular application. So that means every user who wants to use that needs to be very skilled in that math and also in coding to be able to do that. And that would immediately shrinks the audience to a very tiny fraction of potential users. Right? So this can also be seen from our users. So you know that Gurobi has callbacks where the user could write heuristics and cutting planes and stuff like that. But from our users, only a very small fraction are using callbacks, and most of those who are using callbacks would only do that for informational purposes, like getting the messages or being able to terminate the solve sometimes. And then those people who are actually doing stuff like separating cutting planes or lazy constraints or primal heuristics, this is really a tiny fraction of our users. So, and I don't think that you can make such a big commercial success out of that. So a different story would be specific applications. So code for specific classes of problems like vehicle routing, there, of course, you would implement a solver that would use branch and price to solve the problem. But then again, the user wouldn't need to implement anything difficult. They would just use this, whatever application it is, and plug in their application data. That is something that I can imagine could be successful if the application is important enough.
Mm-hmm. Yeah. How to come up with default parameter values for a solver?
Yeah, that is where the 192 machines come into play. So there's this lots and lots and lots of tuning. So in the end, so you have a gut feel of what could work well. And what happens a lot is you try it and you see that it doesn't work. And then you try the opposite, and sometimes the opposite works. For whatever reason, you don't know. It's just a matter of fact that with these 6,000 problem instances that we have in our test set, we can run them with 5 random seeds if the cluster is completely free in, I don't know, like 12 hours or something. And then you just see it and you measure it. So this is then more an engineering task than really science. This is tough. But of course you always have ideas like, yeah, I don't know, if it's a very big problem, then use that. If not, use something else. If it's a pure binary problem, then maybe probing is more important, and then you try these ideas and implement them in the automatic settings of the solver.
Mm-hmm. Very interesting. A lot of experimental work, and I was imagining something like in that direction. And how to extract the best from the solver? I mean, how to go beyond its default settings to try to achieve a better performance?
Yeah, so one thing, of course, when you just want to use parameter settings, then a very good thing is our tuning tool. So CPLEX also has this tuning tool, and I guess Express has. Yeah, Express I know has something similar. So this is kind of a global optimization task, right? Where you have this parameter space, and for every parameter combination, you want to assess what is the performance, and then of course you have your set of problem instances, and then it would run. And the nice thing about that is that parallelizes very well. So if you have like a large cluster of machines, then the speed up that you get in the tuning process is almost linear with the number of machines. So this is a nice thing. The bad thing is that this is a very difficult problem. So to find a good parameter combination. But for some problem classes, it works well. So, but of course, you should not tune on one problem instance. You should tune on a set of problem instances. Otherwise, you run the big risk of over-tuning and just get random luck on those. Other than that, the main thing I'd like to stress is before going into parameter tuning, you should really try to improve your model. Right? So that is tough, in particular when it comes to numerical issues. So if your model has numerical issues, then often it's not only that you get kind of strange answers, it is also degrading performance usually very much. So try to find and that is the art of mathematical modeling. You need to try to find a model that describes the reality kind of well enough, but is simple enough and numerically stable enough for the solver to perform well. And that is always a challenge.
Uh-huh.
So this is also our main struggle when we want to sell solver software, because then there's always the task that the user basically has to do, or a consulting company has to do, which is to create that model. And if that is bad, then they would see bad results.
Mm-hmm. Yeah, and talking about that, can you cite some myths and pitfalls regarding MIP solvers and even mathematical models too?
Yes. So the one thing I'd like to mention is that people really always struggle with understanding the meaning of the feasibility tolerance. Right. So this is a tough concept, because the feasibility tolerance, which is in Gurobi and also in Simplex by default 10 to the minus 6 in absolute terms, it is not identical to a theoretical MIP model where you just increase the right-hand sides of all your inequalities by 10 to the minus 6. It means that in that there is this gray area where the solver can arbitrarily decide that a given solution is feasible or not, right? So it means everything that is strictly speaking feasible needs to be detected as feasible. Everything that is infeasible by more than the tolerance has to be marked as infeasible. But everything in between, the solver can arbitrarily choose, and this then highly depends on where this is slight infeasibility is detected. Is it pre-solved? Is it in the simplex solver? Is it wherever? That it can change. And that means that two answers, namely infeasible or feasible, for the very same problem can both be correct, right? And that is completely strange. So people struggle with that. And that, of course, this is the most extreme case, but it can also mean that a solution of 10 and a solution of 100 can both be optimal and both be correct because of that strange definition of the feasibility tolerance.
Yes,
but there's no way around it. And that is really hard for users to understand, in particular when they have numerically unstable problem data.
Yeah, I've been through that. I completely understand what you're talking about. Yeah. So Tobias, some people may wonder if commercial solvers like Gurobi support the use of GPU. I saw a recent post by your colleague Greg Lochner from Gurobi, in which he explains why this technology has not been embraced by you guys, for example. But I would like to hear your thoughts on this.
Yeah. So the we are still not using GPUs, and that is a question that comes up all the time when we talk to users or other people. The main problem is that the core arithmetics that we do is in the simplex algorithm. This is sparse algebra, right? So sparse computations, and that is not what GPUs are made for. So and it's actually usually a large series of small computations, and each computation depends on the result of the previous one. So just putting one of those on a GPU, that is more overhead in the data transfer than actually doing them. But then there are millions of these steps, and each depends on the results of the numerical results of the previous one, not on logical things. And that is tough for a GPU. So we have never found a good way to use the GPU for these things. So of course you could think about, at some point in the LU factorization, there's a dense core block that you can exploit, and we do that. So this is where then AVX and SSE CPU instruction sets come to play, and we also have like 3 different solvers there, basically a fully dense, a half dense, and a sparse version of all of the algebra, of the linear algebra. But still, typically, these dense blocks are still so small that it's not worth it to send that to a GPU to do that.
Mm-hmm. You already mentioned your work on conflict analysis, but other than that, how can constraint programming enhance the performance of MIP solvers?
Yeah, so I think we already use a lot of techniques from constraint programming, and in the MIP world, you would just call that domain propagation. And then, of course, conflict analysis. I think the most important part of constraint programming is not necessarily the algorithmic piece, but the expressiveness of the modeling language. And that is tough. So we have started to do something a little bit with what we call the general constraints, so that you can just write down indicators or max, min, or piecewise linear or so, and that will then automatically get translated into a mixed integer linear programming formulation, potentially with special ordered set constraints and all alike. But we don't have these fancy, in particular, scheduling constraints or all different or stuff like that. And when I say scheduling, then maybe that's also a thing. That is an area where we could benefit from constraint programming, because this is pure scheduling problems. Those are one of the few where constraint programming solvers are really, really much better than mixed integer programming solvers. So we could potentially then go into the constraint programming mode or in some heuristic to do that.
Yeah, I'm
But
not
this
sure.
is something that we've never tried.
Yeah, I'm not sure if you if you are aware of the recent paper by Ruben Ruiz and other co-authors where they compare the performance of MIP solvers and constraint programming solvers when solving classes of scheduling problems. And they have shown that in some cases constraint programming seems to perform better.
Yeah, that's I don't know that particular paper, but I have read a few similar ones. The struggle here is that in order to do really a good comparison, you need to have usually then multiple authors, each one being an expert in their domain. So like you have to, it very much depends on the model. So and this constraint programming model is completely different than the MIP model, and you have to have a good constraint programming model and you have a good MIP model, and only then you can do a fair comparison. So there are some papers who would just take the constraint programming model and with a very stupid MIP model as a direct translation and compare it, and then the constraint programming is faster, or the other way around, you take the MIP model and then just use a constraint programming solver on these linear constraints. Of course, that's stupid. You would model it completely differently in a constraint programming framework. And only if you do it both ways in a good way, only then you can have a fair comparison.
Yeah, I see what you mean. And what about machine learning? In your opinion, what are the main opportunities for using machine learning to improve the performance of MIP solvers?
Yeah, so what I like best, and what we already did a few times in the past, is to use machine learning techniques to find good rules that will then become part of the default parameter settings, but then not using the machine learning piece just to understand the rule and then implement it from scratch. And for that, it is very important that you have this, what is called this explainable machine learning, right? So you just don't want to have a big mess of a network that gives you something when you put in something. You want to have something that you can understand, which is, for example, true when you use decision trees, then you can understand, at that point, it looks at this feature and it goes either it's smaller or larger, and then it does this and this. And this is something that we use for some places. So for example, for the decision whether to dualize or not a linear program, and if you dualize it, whether then to use the primal simplex or the dual simplex. We used machine learning to basically identify the best rule on our test set. And there are other examples for that. And the other thing, which is maybe not directly machine learning, but of course related, is this generative AI, which I think has a large potential to help us in particular to overcome the difficulty of modeling a problem. So the dream, of course, for us would be that you can take such a tool and just state here, I have a supply chain problem and my resources are this and this and this, and my constraints are this and this and this. It costs me so much to go from here to there. And then the generative AI would automatically produce a mathematical model or a Python code out of that you can then take as a starting point, and then as a human start to refine it and potentially fix it. Of course, they make mistakes and then have a starting point to start your model. So the hope would be that this makes the usage of a math programming solver easier, so that more people can actually start using it.
Exactly. That was exactly my next question. That it's no surprise to hear people complaining about the difficulty of using optimization tools, especially when compared to AI and machine learning packages, not only because it requires one to have a decent background in mathematical modeling and perhaps even in integer programming, but also due to the complex nature of optimization problems. And are we any close to improving the situation, perhaps benefiting from the substantial advances of generative AI technologies, as you just mentioned?
That's exactly. So this is the big thing in our world, I would say. There is this barrier for using a math programming solver, which is that you basically need a master's or a PhD in operations research or math or whatever to just be able to formulate your problem in mathematical terms. And if any proposal to make that easier will make our field more successful. And generative AI is one of the potential candidates to be able to deliver that. So, but of course, many people are projecting many hopes on that right now. So we'll have to see how much this can deliver.
Yes. You once told me that one of your biggest weaknesses is not to be so aware of what is out there. Perhaps this can be seen as an advantage because this may give you some room for trying out, ideas that are out of the box.
Yeah, that's true. So I always try to. So I'm very much interested in solving problems. So in having an idea and then thinking it through and come up with a good way to solve it. And I'm not so great in knowing what's out there, reading papers, following the work of other people, and that is a struggle for me. Which is why I then need collaborators who know that much better. And so I'm very bad at picking up other people's things and then extending it. I always want to do this myself. And this is I enjoy it the most. I want to do it from scratch myself. Of course, which you can think of as kind of reinventing the wheel often, but then it's also, as you said, a chance that then something else comes out of it that other people would probably in the details not have considered.
Yeah.
But when I write a paper, which I sometimes still do, then that is the biggest struggle for me to write kind of the introduction with the literature overview and to be fair to other researchers to not miss what they have done.
Mm-hmm.
So this is tough, and in particular this did happen in the beginning of my SCIP research when I was not aware of John Hooker's work, and then only later came when I met him at a conference that he was also doing pretty much the same thing, not as applied, so as like hacking away and producing 100,000 of lines of code, but the ideas were the same, and he also had a software framework to do that, and that was kind of a pity that it would have been also nice to directly collaborate with him, but we didn't because I just didn't know.
Uh-huh. All right. To conclude, do you see yourself doing anything else in the future other than working on MIP solvers?
Well, in my professional career, maybe not. If it doesn't work out anymore, if maybe I'm at some point frustrated or whatever, or I cannot contribute anymore, then I guess I could also enjoy going into the applications, like going to some company who is developing some optimization-based solution for a particular application, where I can then kind of bring in my expertise about the guts of the solver, and I know how to get the most out of the solver because I know how they are implemented. So this is also something that I could enjoy, I think. Yeah. But for now, I'm really still so much into the core of the algorithms, of the solver algorithms, that I don't think about that a lot.
Okay, Tobias, thank you so much for your time. It was incredible. Thank you so much for the very valuable insights. It was also fascinating to learn about your story, the story behind SCIP and other innovations like strong branching and the conflict analysis and, all those things. So, I cannot thank you enough.
Yeah, thanks, Arno. So it was a lot of fun to talk about all that. So thanks for inviting me.
Yeah. I know you have lived in Berlin your entire life. If you're considering spending a sabbatical somewhere, Brazil is an option. So.
Yes, why not? Why not?
Yeah. Just let me know and we can arrange something in the future.
Yeah. Thank you.
Thank you. So take care. See you soon. Danke. Bye. Ciao.
Goodbye.